Hi everyone. Thanks for joining another episode of the IGS Global Seminar Series. This is going to be the last seminar of sort of this season. We're going to take a break over summer, and the plan is to pick it up in the autumn again and carry it through next winter. This week we have another seminar on sea ice. So we've got Dr. Arttu Jutilla. He's currently a postdoc at the Alfred Wegener Institute in Germany, and he's going to be giving us a talk on recent observations during the Winter IceBird campaign that they just completed. And then we have Dr. Mark England, who is now a senior research fellow at University of Exeter, who's going to be talking about climate models and spurious impacts of sea ice loss in climate models. So I'm very excited for both of these, and thank you all for joining again this week. And without further ado, I'm going to pass it off to Arttu.
All right, thank you. Let me share my screen and start with this. Hopefully you can see the correct full screen presentation.
Yep, looks good. And maybe just before you get started, I'll just mention we'll save questions until the end of each of the talks. So if you have questions, drop them in the chat, or just hold on and we'll do a round of questions at the end of Arttu's talk here. So there you go, take it away.
All right, thank you. Thanks for the opportunity. The talk this evening is about the multi-sensor airborne observations of Arctic sea ice, and it's the AWI IceBird program. We just finished a campaign. We came back from it last week, actually, and in that sense, I have a confession to make. I don't have that much recent results to show from that yet, but I'm going to hopefully make it up to you in other results and research highlights. So the outline of this presentation is first to introduce the IceBird program to you, then why it is such a special thing about the unique sensor configuration, show you some examples of data that we have, and then those research highlights. But we actually start with a little sneak peek just for you. This is, I think, coming as a press release tomorrow. We are actually celebrating an anniversary of 30 years of airborne measurements over sea ice at AWI. So what started mainly as atmospheric measurement campaigns in March 1993, when I was 1 year old. They had a single beam laser altimeter on board the Polar 2 and 4 aircrafts back then. And then 30 years later, again in March, this time 2023, we finished our IceBird Winter campaign, this time with a lot more instruments on board our aircraft Polar 6. So a little bit about the IceBird project. It is a long-term program of airborne campaigns that were previously called with several different acronyms, and we decided to make things more simple and cohesive and put them under this IceBird umbrella. So they are for direct observation of sea ice thickness mainly, but also some additional physical parameters, and they are targeting the winter maximum and summer minimum of Arctic sea ice. So therefore, there is two campaigns, one winter, one summer. The winter campaign concentrates on the winter sea ice thickness time series, additionally on snow depth measurements, and these are then used for quality control and validation of remote sensing data. There are the three primary sensors, which is the IceBird, laser scanner, and snow radar, and I will go into these a bit more in detail in just a moment. The counterpart for the winter campaign is the summer campaign, obviously measuring the time series of summer sea ice thickness, but then as snow has mostly melted away, they concentrate on the melt point coverage. So snow radar is switched to nadir camera for calculating melt point fraction. And in this presentation, I concentrate mostly on the winter campaign, just as it includes the most of the sensors that there is, and that's the one that I was just participating in the last month. So the airborne measurements take place usually from Svalbard to Alaska, covering the Western Arctic Ocean, based in Longyearbyen, Station Nord, Alert, Eureka, Resolute Bay, Inuvik, and Utqiagvik. Nowadays, they are based on the Basler aircrafts that we have called Polar 5 and Polar 6. And the thing that sets these IceBird campaigns apart from all the other airborne surveys that there are around the world is that with these aircraft, we are able to go slower and lower than others. And this has some definite benefits for us and for the measurements. And compared to 30 years ago, now we carry a lot more sensors. We have electromagnetic induction sensors, radars, lasers, photogrammetry. Those are the ways that we actually measure the sea ice. The party piece, if you allow, is the IceBird. It is the electromagnetic induction sounding instrument. It looks like a torpedo. There's a schematic on the right side of the screen. It is lowered from the aircraft with a winch. It's towed on a cable, and the instrument itself it's basically like a big metal detector. With those electromagnetic induction sounding, it senses the electrically conductive surface, which is the seawater. And this relationship can be then transformed into the distance between the instrument and the seawater, which is the sea ice bottom. On the sensor, there is also a laser that measures the distance to the sea ice surface. And then when you subtract one from the other, you get the total thickness. This is an important distinction. It is the sea ice plus snow thickness. So this instrument cannot actually distinguish what is sea ice and what is snow, but that's the total thickness. The footprint of the instrument is about 40 meters, and the accuracy of the thickness measurement over level ice is 10 centimeters. And this kind of instrument has been flown since 2001 with helicopters, for example, from our research icebreaker Polarsten, and then since 2009 with our fixed-wing research aircraft Polar 5 and 6. The other main instrument is the snow radar. This is probably familiar to some of you. It is comparable to the snow radar on the NASA Operation IceBridge. It is developed by Cresys. It is an ultra-wideband frequency modulated continuous wave radar, as it is known with its full name. It is quad polarized, so it's both transmits and receives in both vertical and horizontal polarization through the 2 to 18 gigahertz bandwidth. And with this radar, it is the same bandwidth as on Operation IceBridge. Theoretical range resolution in snow is 1.14 centimeters, but where we actually do better than Operation IceBridge comes from the fact that we fly lower and slower is the footprint size. So our snow radar footprint is just a few meters across in diameter. And also our sample spacing is smaller. So on the bottom there is three figures in different processing steps, how the radar data looks like. The horizontal axis is along track distance in kilometers, and the vertical axis is range in snow. And if we concentrate our eyes on the panel C on the right-hand side, which is the most clean one, there you can see the change from black to gray. That is the change from air to snow. And then there is some bright whitish color slightly below, and that is then the interface between snow and sea ice. So then the distance between those two interfaces can give us the snow depth in the end. The third main instrument is the laser scanner, from where we get the snow freeboard. And again, flying slow and low pays off with a lateral resolution of up to 25 centimeters. And I could watch these segments of sea ice surface like days on end. I find them really, really pretty, and the amount of detail that you can see there, it's just magnificent. So that was a quick overview of the sensors on board. And if we take a look on the schematic again, so the aircraft itself flies just 60 meters or 200 feet above sea ice, and the IceBird instrument is lowered on a cable flying 15 to 20 meters, so 40, 50 feet above sea ice, taking those measurements. So after these surveys, these measurement flights, we have a unique data set where we measure simultaneously the total thickness, the freeboard, and snow depth. Coming to some example results from previous campaigns. This is the winter campaign from 2017. And there are three panels. Left one is the total thickness from the IceBird. The middle one is the snow freeboard from the laser scanner. And on the right is the snow depth from the snow radar. The thin red lines are the flight tracks, and then the background there is the sea ice age. So the brighter, whiter colors mean older sea ice. So I think the best thing is to actually straight away compare to the campaign we did in 2019, similar way, and compare the differences. And there we can see that on the left panel, if we compare the total thickness, everything we measured was first year ice with modal thicknesses under 2 meters. And then, of course, when we reach the more multi-year ice regions, then we get thicknesses up to 10 meters or more. And along there, also snow freeboard and snow depth increases. But what I found really interesting in this required actually looking into the past and considering the conditions before the 2017 campaign, which was actually the reversal of the Beaufort gyre. And the Beaufort Sea was actually ice-free in 2016. Which meant that then the following winter, the multi-year ice couldn't actually penetrate into the Beaufort Sea, but instead was pushed against the islands of the Canadian archipelago. And I think that is reflected also in the snow freeboard. So if we take a look on the flights over the Beaufort Sea, we see a wider spread on the snow freeboard values, indicating more rougher sea ice, which then again captures more snow. So the snow thickness in 2019, which is the panel on the bottom right, shows very, very little snow over sea ice. But then again, 2017, there was a lot more. So my conclusion is that there was rougher, more deformed sea ice due to the reverse Beaufort gyre, and that's captured more snow. Some research highlights. With these measurements, we are able to follow the interfaces throughout the transects in regional scales. So we can follow the snow thickness, we can follow the ice thickness, we know how high up the ice floats, we can see the freeboard. And here is an example segment, just some 25 kilometers in length, also happens to be the distance corresponding to a satellite data grid size. And you can see the variability of both ice thickness, snow thickness, the deformation, fraction of level ice, and it's quite remarkable. And all of these, the snow thickness, freeboard, ice thickness, they are important on their own. But if we put them together, we can actually do a bit more with them. And we can actually start deriving some more properties of the sea ice. As is usually the case in altimetry, this freeboard to thickness transformation is used. So altimeters measure the freeboard value, which is then used with assumptions of snow thickness and densities to turn into ice thickness. But here, because we measure all of them separately with different instruments, we can actually use them to calculate one of the unknowns, which is the ice density. And here's the lower panel showing the same segment and the corresponding ice density values. And my work recently collected all these measurements from 2017 and 2019, and I calculated the sea ice bulk density values and compared them what is used quite broadly in altimetry. And there are quite some differences, but there is also some definite differences in the methods or what is included. So the most commonly used values in Alexandrov include only level ice, whereas we included everything, also deformed. But most exciting thing here is that the multi-year ice density is actually based on measurements and not just literature values. So with these, then I was of course looking for a way to predict density and find a parameterization using something easy to apply, simple, single variable. And I found one reasonably good from sea ice freeboard. And of course, one wants to fit a curve to it, and a exponential relationship seemed reasonable. And I think there is potential in here to improve satellite-based sea ice thickness and volume estimates. For example, if this equation is then put into sea ice freeboard, we can actually derive maps of sea ice density instead of using just fixed values, because we know that it is actually not constant, but actually varies. But we don't have direct measurements that are actually valid in time and space throughout the seasons. Another highlight I want to show here is actually from the counterpart summer campaigns. It is showing the summer ice thickness in the southern transpolar drift, so in the Front Strait area. There is a time series on the right figure showing the modal thickness of the IceBird measurements done in different years, and also a modeled values when these surveyed ice are backtracked and then modeled what their thickness should be. And there is quite a difference in 2016 in those values. And my colleague, Jakob Belter, then went back to investigate what would be the reason. And he actually found out that those ice pieces or backtracked ice parcels originated from areas that were affected with Atlantification. So a lot of warm Atlantic water affected those ice parcels. They were identified through moorings, which are the green dots on the map on the left. And the periods when they were affected is the red part of those backtracking lines. And the outcome here is that even these mechanisms affecting ice growth, they can be seen at the sort of outlet, the exit of the ice years later at the Front Strait. I think I'm closing up on my time available, so I will finish up by listing all the campaigns that have been done under IceBird. There is quite a list of past campaigns on the left. Unfortunately, there is a COVID-sized gap in the recent years, especially in the winter campaigns. However, we are resuming our efforts. There are scheduled IceBird campaigns coming up. There is a summer campaign this year, and then the next winter campaign will be a Canada special, focusing on the Canadian part of the Arctic. On both of those campaigns, the leader is Christian Haas, so you may contact him if you have any questions on those campaigns. We are proposing annual campaigns, but these campaigns are planned in a 2-year window, I think. So we don't know yet beyond 2024 what will happen, but we very much would like to continue our monitoring efforts. So we have added a few lines to the map. These are the surveys that we were able to do in this winter campaign. We managed to cover the key areas that we wanted to cover so that we can actually continue the time series of CS measurements. Unfortunately, the processing of these measurements will take yet some time. So this is the extent that I can show from this campaign. And since I'm talking to you from the Alfred Wegener Institute in Bremerhaven, I will put a little cheeky advertisement about the upcoming CS Symposium in 1 month here in Bremerhaven. I think the registration is still open, so visit the website for more information. And when you are scrolling through the internet, please visit our IceBird project webpage and also the newly revamped Sea Ice Portal webpage. Thanks for your attention.
Great. Thanks, Arttu. Thanks for the great overview. Open it up to any questions. Alec.
Yeah, maybe while others are deciding their questions, one kind of overarching one and one kind of more specific one. So the overarching question, like how do you decide on each kind of annual campaign's priorities? I mean, are you trying to revisit the same places? Are you trying to maximize satellite underflights? Are you trying to just complete coverage of the Arctic? Like how do the funders kind of expect IceBird to be profiling, and how might that evolve in the future? Do you know?
Right. So of course we would like to cover as many regions as possible, and from there it's really in the end, well, we have a lot of options for flights. We take into account satellite underflights and also repeat surveys from past years, and really looking into SAR images about the ice conditions if there is something really interesting that we want to survey. But when it comes to the actual campaign, then we have a limited time, usually 4 weeks, about a month, and we are at the mercy of the weather, so we can't really fight that. So we try to find the best balance.
Cool. Then yeah, maybe just another quick one was yeah, you talked about the differences in density between your approach and the Alexandrov results, which I found obviously super interesting for our altimetry work. I'm just wondering, you kind of show the standard deviations or the uncertainties of both of those, and you know that they're kind of broadly consistent when you factor that in. So I'm wondering how much you do see that as a kind of a bias, or do you see it as potentially just, you know, we need a better account for the uncertainties and sampling differences and things like that?
Yeah, like for the density stuff, like I could talk more and more about it. But like there are like some main differences that Alexandrov calculated. For example, the first year ice measurements, they use the Soviets airborne surveys. So the measurements are actually mostly done around runways, which is level ice, of course, for aircraft to land. So it's actually not including deformed ice, whereas we do. So there is seawater inclusions and ridges and everything included. So yeah, is it a bias, or is it just measuring slightly different thing?
Mm-hmm.
But then mostly I'm sort of concerned or worried about the multi-year ice, which in the Alexandrov paper is taken from literature. So they just take typical values and calculate the submerged part of ice and above water level ice, and for that they chose, I think, really low value of 550 kilograms per cubic meter, which is, I think, really rotten summer sea ice.
Right.
So now we have actually some measurements to support that, but there again, like the multi-year ice back when that paper was written and compared to now, the multi-year isn't as multi as it used to be back then. So there is that kind of difference as well. So it's, even though it might seem rather simple that there is differences in the values, but they might be actually coming from different sources and reasons.
Yeah, super helpful to have these new insights. It's really cool.
Great. We'll wrap up with a question from Stephen.
Yes. Do you infer the snow density?
No, we do not. So that one is assumed.
And what do you assume?
So for that, we take, I think it's 300 or 320 kilograms per cubic meter, because the flights are done in April, the winter ones.
Perfect. Okay, well, thanks so much, Arttu. And I'm sure most people on this seminar will be looking forward to seeing the results from 2023 once it's out.
Working on it.
Yeah. All right. Perfect. So we'll move over to Mark.
Okay, great. So hopefully, can you
Looks
see
good.
this?
Yeah.
Okay, beautiful. Yeah, first apologies. I'm slightly losing my voice because I have a cold, but hopefully I can get through this okay. So yeah, I'm a senior research fellow at University of Exeter, and I'll talk to you a little bit. I guess there's a bit of a kind of larger scale thinking about sea ice. So we're looking at the spurious climate impacts of sea ice interventions. What are they, and how do we avoid them? And this is work done with Nicole Feldl at UC Santa Cruz, Ian Eisenman during my time at Scripps, and Till Wagner as well. And the idea here is there is a lot of interest, both within the scientific community and within the broader public, about trying to understand the climate response to sea ice loss. So how does sea ice loss kind of reverberate around the climate system? And the way that this is normally investigated in comprehensive GCMs is to look at kind of compared to experiments. The first is a simulation, normally a time slice simulation, where we have sea ice. This time we're looking at Arctic sea ice from some control period. You could imagine present day or pre-industrial, and then compare that to a simulation with future sea ice, so projected end of the century sea ice from CMIP, for example. And the idea here is that these simulations are identical apart from the sea ice. So they have the same CO2 forcings, but the sea ice is being perturbed to be different. So we can then take the difference and try to understand, well, what is the role of sea ice in the climate change that we simulate? And the coupled experiments show a substantial climate response to imposed sea ice loss. So this is from Skriner et al. 2018, where they compare, these are 6 different models, kind of using a variety of different methods, but showing consistent results for the zonal mean atmospheric temperature, showing a enhanced surface-dominated polar warming in response to Arctic sea ice loss, and also the hint of a kind of a global signal. So this involves some tropical upper tropospheric warming associated also with the sea ice loss. In addition, because sea ice loss is going to impact the meridional temperature gradient, it also has an impact on the mid-latitude tropospheric jet. And so these studies normally find an equatorward shift of the mid-latitude jet in response to sea ice loss. And some of my previous work, we've looked at the tropical response to projected sea ice loss. And so we find that in response to both Arctic and Antarctic sea ice loss, there is an enhanced warming and an increase in precipitation in the equatorial Pacific. So the kind of response to sea ice loss is, it ranges much further from the poles, and it actually has quite a substantial impact and contributes to the kind of projected changes. But the first, for the first part of this short talk, I'll talk about a paper I did with Ian and Till which was published in Journal of Climate back in 2022, where we kind of introduced this idea that some of these methods used to perturb sea ice in these coupled simulations might be having spurious effects. So there's no one best way in which, in these coupled simulations, in which you perturb the sea ice without changing CO2. So there broadly are three methods. The first is albedo modification, and this is some variety of reducing the albedo through changing sea ice parameters in the model so that you absorb more incoming solar radiation, and that will melt your sea ice to some desired amount. The second is a kind of a brute force method of ghost flux, where you add a long wave flux into the sea ice model, unseen by other components. And then the third is some variant of nudging, where you, for example, you could remove certain sea ice for a relaxation timescale to get to constrain it to a desired state. And in this paper, we argue that although these kind of seem quite different approaches, they all have a common limitation, and that is they all add heat into the climate system. And so for the ghost flux, this is quite obvious. You're adding a long wave flux, so you're definitely adding heat into the climate system. But a nudging, by removing sea ice, you're going to be adding latent heat in. And for the albedo modification, although it seems like you're not adding energy into the system, because you're changing the surface albedo of all of the sea ice, you're going to be absorbing a lot more solar radiation at the very highest latitudes, and that's going to result in a extra heating. So the idea here is that this kind of spatially varied heating is going to generate its own climate response separate from what we're trying to examine, which is the response to sea ice loss. And to illustrate this, I'm going to use a very idealized model. This is an energy balance model, which is an aquaplanet, so no land, is a zonally uniform approximation. So it has an ocean mixed layer, and sea ice is present when the surface is sufficiently cold. It has seasonal and latitudinal variations, and the sea ice will melt and grow based on the physics from the Eisenman 2012 single column model. And for our purposes, thinking about the effects on climate, well, in this model, sea ice affects climate in two ways. The first is through the sea ice insulation, and that depends in this model on the sea ice thickness. And then the second is through the surface albedo, and that depends on whether there's sea ice present or not, right? Whether there's sea ice or open ocean. And the governing equation for this model, which it simulates the evolution of the enthalpy, and that's going to determine the surface temperature, it's going to determine whether there's ocean present or ice present, and it's going to determine how thick that ice is. And I won't go into the kind of the details. You can see it in a paper if you're interested, but there's this balance between the absorbed solar radiation, which is going to depend on the surface albedo, a linear representation of the outgoing long wave radiation, an approximation of the atmospheric heat transport, as well as some other terms, including F, which is the climate forcing, which is a kind of simplification of increased radiative forcing from increasing CO2. And for our purposes, the really nice thing about using this idealized model is that we can do this trick where we take the annual mean, and here I'm denoting the annual mean by the overbar, and I won't go through the derivation of this, but in the annual mean, the only impact of sea ice loss is through changes in the surface albedo. So all the input from the sea ice insulation has dropped out. And so by taking the annual mean, we've kind of removed the effect of sea ice insulation. We don't need to worry about that anymore. It's still important for the seasonal cycle, but for the annual mean, it cancels out. And so the only thing which remains is surface albedo to influence the climate. And that is great because by specifying the albedo, which is easy to do in this model, we can isolate the true role of sea ice loss, at least in this model. And then we can use that as a benchmark and compare that to the different methods, which I talked about earlier, and see how they perform, because then we have the true answer to compare against. And so to start off, we have a control experiment. We compare that with a future experiment where we increase the climate forcing to 3 watts per meter squared. And the difference between those two will give you the total warming. And then we take the albedo from the future simulation, but we keep it with zero climate forcing, and that's the specified albedo simulation. And then the difference between that and the control is going to be the role of sea ice loss. So this black line here is the total warming, here showing you the latitude on the y-axis. This is the total warming after an increase of 3 watts per meter squared. And you can see it's polar amplified, and we can decompose that into the warming from sea ice loss alone, which is the gray line here. And this makes sense because all of the polar amplification in this very idealized model is coming from sea ice loss. And then the difference between the gray and the black line is the non-ice factors. And you can see that's latitudinally uniform, which kind of makes sense in this very idealized model. And so we're going to use this gray line as a benchmark, and this is what these different methods should be kind of hitting. But what we find is when we implement these different methods in this idealized model, they all look like each other, which agrees with the literature. They're kind of consistent with each other. You can see these colored lines here, but they all overestimate the role of sea ice loss. So they're much larger than the gray line by about a factor of 1.5 to 2. And instead, in the Arctic, they're actually, they say that about 100% of the warming is due to sea ice loss. And so in this part, I've introduced this idea that in this EBM, the advantage of using it is A, it's very simple to understand, and B, the only annual mean effect of sea ice is through albedo. And so that allows us to kind of isolate the exact role for sea ice in this model. And we find that all of the standard methods used previously in the literature to isolate the response to sea ice loss overestimate the annual mean surface warming attributable to sea ice loss by about a factor of 1.5 to 2. And so, one implication could be that the climate impacts associated with sea ice loss in previous GCM simulations could also have been overestimated. And that's kind of an interesting finding because, well, there's a current debate within the community that perhaps these models don't have strong enough feedbacks and are in fact underestimating the response to sea ice loss. And so what we're saying actually kind of runs a little bit counter to that. And of course, this is a highly idealized model. So it lacks many important processes for the real atmosphere. So for example, the atmospheric moisture, clouds, circulation changes, there's a very long list of things we've idealized away. And so one question is, how do we interpret these results in the context of the real world and in the context of comprehensive GCMs? Second limitation is that we could only really examine the surface temperature response because that's all we simulate in this energy balance model. But we're interested in many other aspects of the climate response, so such as the mid-latitude circulation and the tropical precipitation. And I guess the third limitation here is that we don't offer, an alternative method or a way to fix the existing methods. And so all of those limitations lead to this follow-up piece of work here, which is what I'll talk about in the second part, which is how do we avoid these spurious climate impacts? And this is work I was doing with Nicole at UC Santa Cruz. And so the aims here are to bridge the gap between the results from the idealized energy balance model and bring it much closer to the comprehensive state-of-the-art GCMs. The second is to be able to say something both by quantifying and by looking at other aspects of the climate system, such as the mid-latitude jet, which we couldn't do in the energy balance model. And the third is to kind of propose a framework for correcting existing coupled simulations so that they can remove what we're calling the spurious effects of model intervention. There's quite a number of simulations which exist already, and so being able to kind of correct them would be great for the community. And for this, we use the CSM2 slab ocean aquaplanet simulation. And so I won't go too much into the details here because I don't have that much time, but we've coupled for the first time a simple representation of thermodynamic sea ice in this configuration. So we have CSM2 CAM6, which is the atmosphere component, coupled to this slab ocean with a Q flux and this thermodynamic sea ice model. And this sits higher up the complexity hierarchy, much closer to comprehensive GCMs, but still it allows us a kind of test bed to play around before moving on to the state-of-the-art GCMs. So we perform a number of targeted experiments using this model. The first is a control and a future simulation where we have one time CO2 and then we increase CO2, and then the difference between those two simulations A and B are going to be the total response to the increase in CO2. The third is the ghost flux experiment. So here we implement this ghost flux. The blue is the sea ice area and the sea ice volume, the seasonal cycle of that from the control simulation, and the red is from the future simulation. And so the idea here with the ghost flux is we're trying to mimic both the area and volume from the future simulation, but without changing CO2. And we do that by applying 10 watts per meter squared in this masking shown in yellow here on the right. And so we're able to both get the sea ice area and sea ice volume using this method. And so if we take the difference between C and A, that is what is traditionally estimated to be the role of sea ice loss on the climate system using this ghost flux method. But the way we're thinking about this is that this ghost flux estimate contains the actual role of sea ice plus some spurious role of ghost flux, because you're heating the climate system and it's going to respond in some way. And so if we rearrange this and we assume additivity, we can estimate the actual role of sea ice loss by having this ghost flux estimate and then calculating what we think is the spurious role of ghost flux. And we do that by adding a ghost flux and not letting the ice change. So that's the idea. So what would happen if we heated in the same regions, but the ice didn't change? And so we do that with experiments D and E. So these are new experiments. They both have prescribed ice, so prescribed thickness and prescribed concentration. Simulation E is identical control except for fixed ice. And simulation D is identical to E, apart from we're also applying this ghost flux. And so the difference between D and E is the spurious role of ghost flux. What would happen if I heated the climate system, but I didn't let the sea ice change? And so that's what we're kind of want to subtract out. And so we can estimate the actual role of sea ice loss by subtracting that out. That's the idea with this new framework. And then for completeness and to see how well this method kind of adds up, we can estimate the role of CO2 forcing by having another simulation where we fix the ice but increase the CO2. So that's the role of CO2 forcing absent sea ice loss. And the first result we find here, and what I'm showing is for all different variables. So this is for surface temperature, panel A, for atmospheric temperature, panel B, panel C is for the zonal wind, panel D is for precipitation, and panel E is for the stream function. The solid lines, or the colors, are the estimated response to sea ice loss using the ghost flux method. And the dotted lines are the total response. And so what you see is that they line up very, very well. And so what this says is that in this model configuration, if we use this ghost flux method, nearly all of the total response is apparently due to sea ice loss. So the substantial polar warming, the weakening of the poleward flank of a mid-latitude jet, this mini global warming signal, this increase in precipitation in the mid-latitudes and in the equatorial region, it's all due to sea ice loss, which it doesn't really pass the smell test because we think there should be other non-ice factors at play here. And so using our framework, what we can do is we can estimate how much we think is spurious. So if we focus on panels B and D, where we look at the percentage of the total response for surface temperature and for the precipitation, the yellow is a previous estimate. So this is the estimated role of sea ice loss, which is about 100%. Whereas under this new framework, we're suggesting the orange, somewhere between 10 and 20% of that is this spurious contribution caused by heating the climate system. And then once we subtract that out, in both cases, both for the surface temperature and the precip, the actual role of sea ice loss is only about 80 to 90% of the total response. And if we look throughout the atmosphere, we see kind of an important regional structure, which is important for the story. So the first row here shows the atmospheric temperature. So if we compare what we estimate to be the actual role of sea ice loss versus the spurious contribution, you can see that the structure of this, the latitudinal structure and in height, is quite different. The actual role of sea ice loss, it peaks at the poles, whereas the spurious contribution, it peaks at the sea ice edge. And that makes sense because that's where we're applying the heating to get rid of a lot of the sea ice. And so we're actually having this overestimate in different places than where the sea ice loss is playing the biggest role. And that's actually quite important because where you're heating the climate changes the circulation. And so if we look, for example, at the zonal wind response, which is the middle row, the actual role of sea ice loss is a weakening on the equator, the poleward flank of the mid-latitude jet, whereas the spurious contribution is a weakening on the more towards the equatorward side of the mid-latitude jet. And so this is an area where, because you have this spurious heating in one region, which is near the area of ice edge, you get this underestimate of the circulation response to sea ice loss. And so for this second part of the work here, which I'm just currently writing up for submission, we've implemented thermodynamic sea ice in the new CSM2 aquaplanet configuration. And we hope that the framework we're offering to the community for systematically removing the spurious effects of the model intervention to isolate the true role of sea ice loss, we hope that's going to be a useful addition. And we found that in this model and in this model configuration, the response to sea ice loss was overestimated by somewhere between 10 and 20%. The thermal response, although the circulation changes were actually underestimated. I just want to leave you with one caveat. So you might go away thinking 10 to 20% doesn't sound that bad. But I have a kind of reason to believe that actually that might be a kind of low estimate, a kind of conservative estimate of what the actual underestimation might be. And that's because in this, in CSM2, in this model configuration, which is the slab ocean aquaplanet with thermodynamic sea ice, the sea ice is extremely sensitive to small increases in CO2. So you might have noticed that I only increased CO2 by 15% to get a dramatic sea ice loss. And so that's much more dramatic than the real world or comprehensive GCMs. And so sea ice changes play a really large role in this kind of world. And another way of kind of thinking about that is that in comprehensive GCMs in the past, people have had to apply somewhere around 50 to 100 watts per meter squared of ghost flux to melt the sea ice, whereas in this model configuration, you only need about 10 watts per meter squared. So it's extremely sensitive to heating. And why does that matter? Well, if you live in this regime where ice is a really dominant player in all of your climate changes, and you kind of have an upper bounds of overestimating up to 100%, well, then you could only, like, for example, here, in this scenario, you'd only be able to overestimate by up to 25%. Whereas I think for real world and comprehensive GCMs, ice is an important factor, but it's not extremely dominant as in this model configuration, and that opens up how much you can overestimate your role of ice by a substantial amount. So yeah, I'd like to leave it there, where saying that 10 to 20% I think might be on the low side, but it's also good to inform future simulations. So I'll take any questions. Thank you very much.
Excellent. Thanks, Mark. Lots to think about there. Open it up to questions.
I'll maybe lead us off again then, if no one else has any. Yeah, I'm just wondering what your views are, Mark, on like, you know, your, I guess, like philosophical reasons for constraining the impact of sea ice loss itself. So is that, I kind of agree after reading your papers that, yeah, it seems like that role has been maybe overstated in previous studies. So do you see this work as trying to kind of set the record straight, or do you think there's like, you know, more science that could come out of this once we can better constrain the actual role of sea ice itself?
Yeah, I think part of it is a kind of philosophical approach to the question, to be very kind of declarative before we do these studies about what are we really talking about, because, you know, you have to melt the ice in order to get ice loss, and then you study what the ice loss then does, but then we attribute everything to the ice loss itself. Mm-hmm. But I think this is, you know, it's an important area of research where we're trying to understand how does polar climate change affect the lower latitudes, for example, and the way we communicate that to the public. I think we have to be really kind of careful in what we attribute to different things, because as we've seen in the past, it's really easy to kind of go, the newspapers will go with a narrative about mid-latitude extremes being caused by sea ice loss, even though I think the evidence for that is perhaps very mixed right now. So I think it's really important to, I guess, set the record straight a little bit, but it's, you know, we try and do the best science we can, and we have to be careful about how we frame things.
Well, thanks.
Interesting. Anyone else? No. All right. Well, thanks so much, Mark. Yeah, echoing John's comment there in the comments. Great talks by both Arttu and Mark today. So thanks to both of you guys for volunteering to talk. And yeah, this is the last IGS seminar of the season. So this one will be uploaded to YouTube probably tomorrow. And then we'll start sending out some information later this summer about when we're going to pick things up in the fall.